Good morning, dear student. Today we discuss the next important point of photochemical reaction. So, in previous lecture, we will discuss what is photochemical reaction and what are the different laws for photochemistry. That is, first, that is Groth-Draper law, and second is Stark-Einstein law. So, before discussing the quantum yield, in this lecture we will discuss the process of deactivation with the help of Jablonski diagram. So, our main topic of this lecture is the process of deactivation. The process of deactivation with the help of Jablonski diagram. So, you are very much familiar with this Jablonski diagram. So, process of deactivation, we know that a molecule absorb light radiation, get activated and get converted into the product. So, in this lecture we will discuss the process of deactivation. After goes into excited state, how it will deactivate. So, let us see what is this Jablonski diagram. So, in this Jablonski diagram, the important points regarding to this Jablonski diagram is that it include ground state, excited singlet state and excited triplet state. So, this Jablonski diagram, it is useful to understand the process of deactivation. So, it includes ground state, excited singlet, excited triplet state. Second, in this Jablonski diagram, the excited triplet state, excited triplets have lower in energy. So, why excited triplet state have a lower in energy? We will discuss this point also. And the next important point, that is the process of deactivation. That is, one is a radiative process, and next one is non-radiative process. So, a radiative process and non-radiative process. So, this Jablonski diagram consists of ground state, excited singlet, excited triplet. Excited triplet have lower in energy. Okay, a radiative process such as fluorescence and phosphorescence, and non-radiative process such as internal conversion and intersystem crossing. So, we will discuss all these points regarding to the Jablonski diagram. So, before discussing what is Jablonski diagram and what are the steps in Jablonski diagram, one by one we discuss what is singlet excited state, what is triplet excited state, why the excited triplet is lower in energy as compared to excited singlet state. So, we will discuss this point and then we discuss the Jablonski diagram for deactivation process. So, let us see the first one. So, we will discuss the first one, that is excited singlet and excited triplet state. So, what is this excited singlet and excited triplet state? Let us discuss. Let us see the first case. Case first, that is excited singlet. Case first. So, let us consider this is a electronic ground state. This is your ground state in which there is a two electron. So this ground state is considered as electronic ground state, because here we consider a electron, that is electron ground state, electron ground state. And if you consider here, it is an excited state. So instead of considering the atoms or molecules, we are consider here the electron to understand the process, that is excited singlet and excited triplets. So electron ground state, because electron is present in ground state. When this electron absorb light radiation, that is h mu, when this electron absorb light radiation, that is a quanta of radiation h mu, then what happen after absorption of light radiation? In case first, one of the electron, so you can write here, this is your ground state and this is your excited state. So one electron is remain in ground state while another electron will absorb the energy by quanta, by absorbing the light radiation, and goes into the excited state with no change in spin. So this electron have a spin plus half, this electron having a spin minus half. In this case, by absorption of light radiation, the electron goes into the higher excited state, that is electronically excited states, higher energy state, but its spin does not change. So the spin remains minus 1/2. So if we consider this is a ground state, this is the excited state. So if we consider the spin multiplicity for this excited state, if we consider a spin multiplicity, that is 2s plus 1, here we consider the spin multiplicity. Let us see once again. So this is the case, one electron goes into the, this is your ground state, this is your excited state after absorption of light radiation. So what is spin multiplicity? Spin multiplicity is given by the formula 2s plus 1, 2s plus 1, where s stands for total spin of the electron. So in this case, if you consider this case first, that is one electron goes into the higher higher energy state, but there is no change in spin of the electron. Therefore in this case, if you consider the total spin, that is s total spin, which is equal to the spin of electron present in ground state plus the spin of electron in excited state. So the net spin is equal to 0, and therefore the 2s plus 1 value becomes 2 into 0 plus 1, so which is equal to 1. So this system, that is ground state, excited state, in this system, or the state which having the spin multiplicity, that is 2s plus value is equal to 1, and therefore it is considered as excited singlet state. So therefore it is considered as an excited singlet state, because its spin multiplicity is equal to 1, and therefore this excited state, it is considered as excited singlet state. This is considered as excited singlet state. So this is regarding to the excited singlet state. When two electron is present in ground state, one of the electron will absorb the energy and goes into the higher excited state, but there is no change in spin of an electron, and therefore if you find out the spin multiplicity for this excited state, electronically excited state, then the total spin will becomes 0 and the spin multiplicity is equal to 1, and therefore this excited state, it is considered as excited singlet because its spin multiplicity is equal to 1. Therefore, it is considered as excited singlet. Let us consider the second case, that is case second, that is excited triplet. So we get excited singlet when electron does not change its spin when it goes into the higher energy state. Let us consider again. This is your excited state, this is your ground state. Again, there is a 2 electron, it will absorb the light radiation. So after absorption of light radiations, one of the electron goes into excited state. So one electron is remaining ground state and another electron goes into the higher energy state, that is excited state, with spin change, with flipping of a spin. That is, in this case the spin is minus half, but after absorption of light, when it goes into the excited state, its spin is get changed. There is a spin flipping of an electron and the minus half spin is converted into plus half spin. So the spin is changed in this case. That is case second. We consider excited triplet. Again, we have to find out the 2s plus value, that is spin multiplicity in this case. So the total spin S total, which is equal to the electron present in ground state, it have a plus 1/2 spin, plus the electron present in excited state, it is also plus half spin. So plus 1/2. So the total spin will becomes 1, and therefore the 2s plus 1, which is equal to 2 into 1 plus 1. So here the 2s plus 1 value becomes 3. So we get here a triplet. So in this case we get a triplet, and therefore this excited state is considered as excited triplet. This excited state is considered as excited triplet. Because its spin multiplicity is equal to 3. So this is regarding to the excited singlet and excited triplet. When electron present in ground state absorb light radiation and goes into the excited state without changing spin, then the spin multiplicity is equal to 1 and the excited state is considered as excited singlet. While if electron absorb light radiation and goes into the excited state with change in spin, then the spin multiplicity is equal to 3 and the excited state, it is considered as excited triplet state. So this is regarding to the excited singlet and excited triplet state. So let us see the second point, that is, so this is the first point in Jablonski diagram. It consists of a singlet excited state and triplet excited state. The second point is also important. The excited triplet is lower in energy. That is, excited triplet is lower in energy. As compared to excited singlet. So why excited triplet is lower in energy as compared to excited singlet? So this is according to the rule of spin multiplicity. So rule of spin multiplicity, rule of 2s plus 1, rule of 2s plus 1. So what is the rule of spin multiplicity? The rule indicates that the state with maximum multiplicity having lower energy, that is, the state with maximum multiplicity will have lower in energy. So according to the rule of spin multiplicity, the state with maximum multiplicity is lower in energy. Therefore, in case of excited singlet, the multiplicity is 1, while in case of excited triplet, the multiplicity is 3. So maximum multiplicity in case of excited triplet, and therefore excited triplet is lower in energy as compared to excited singlet. So what this rule indicate? The state with maximum multiplicity. So maximum multiplicity is in the case of excited triplet because its spin multiplicity is equal to 3, therefore it is in lower in energy. So why this excited triplet is lower in energy? Again we see an example to understand why excited triplet is lower in energy. So let us consider a p orbital, that is px, py, pz, and if 2 electron is there, then we put the 2 electron in this way. So 2 electron, again the another possible arrangement is that we can put this electron like this. Another possibility is that we can put both the electron in px orbital. Another possibility is that we can put the electron in px and py orbital with negative spin. So in this case both electron having plus half spin. In this case one electron is plus half, another is minus half spin. So in this case both electron are present in px orbital, both having one having plus half spin, another having minus 1 half spin. So in this case both electron present in 2 different orbitals and both having a minus 1 half spin. So if you find out the value of 2s plus 1 in each case, so in this case 2 into, so 1 half plus 1 half, so total spin will be 1 plus 1, so we get here 3. So its spin multiplicity is equal to 3. So 1 half plus 1 half, so it becomes 1. Okay, total spin, therefore spin multiplicity is equal to 3. So in this case the spin will be 1 half, this having plus 1 half and this having minus 1 half. So total spin becomes 0. So in this case 2 into 0 plus 1. So here we get a singlet. Spin multiplicity is 1. In this case again 2 into 0, because the spin is cancel out, plus half minus half, again here we get a singlet, and here 2 into the total spin in this case, yes, total, which is equal to minus 1 half plus minus 1 half, which is equal to 1. So 2s plus 1, which is equal to 2 into 1 plus 1, which is equal to 3. So in this case the spin multiplicity is equal to 3. So which is a possible arrangement for these 2 electron. So we know that according to the spin multiplicity, the state or the configuration, so in this case we consider a configuration, the state or the configuration which have a maximum multiplicity are lower in energy. So in this case this configuration and the last configurations are maximum multiplicity, therefore they are lower in energy. They are lower in energy because they have maximum multiplicity or greater multiplicity as compared to these 2 configuration. So these 2 have higher in energy. So we can consider that the first and the last configuration is only a valid configuration, or it is only a possible configuration for this 2 electron. This configuration and this configuration, that is second and third, it is not possible because the spin multiplicity is equal to 1, it is in higher energy. So this configuration, it is not possible, this configuration is not possible or not valid, only this configuration is possible and this configuration is possible because the spin multiplicity is higher, and due to high spin multiplicity it is lower in energy. Another reason is that this two arrangement, that is first and the fourth arrangement, is moved towards the stability, that is, if an extra electron is added into the next orbital, then the orbital becomes half filled. So we know that when the orbital is empty, half filled or completely filled, then it will give extra stability to this system or to this configuration to this orbital. It will give extra stability to the orbital. Therefore the first case and the last case is possible configuration. It have a higher multiplicity and which is in lower energy. Therefore excited triplet is lower in energy as compared to excited singlet. So the main reason is the spin multiplicity rule. Higher the spin multiplicity, lower the energy. Therefore excited triplet has higher spin multiplicity, so it is lower in energy. So this is the second point in a Jablonski diagram. So you understand what is excited singlet and what is excited triplet, then you understand what is why excited triplet is lower in energy as compared to excited singlet. So let us see the diagram, that is Jablonski diagram for the process of deactivation. The process of deactivation. So if we consider, this is a energy curve, energy here. If you consider, this is your ground state, this is your excited singlet. So depending on energy, there is a different state, that is excited singlet first, excited singlet second, excited singlet third. So depending on the energy, excited singlet first, this is excited singlet first, this is excited singlet second, this is excited singlet third. So why it is excited singlet? Because the multiplicity is the multiplicity, that is 2s plus 1 is equal to 1, because in this case by absorption of light radiation the electron goes into the higher energy state, but there is no change in spin of the electron, therefore it is excited singlet state. So if we consider here, excited triplet state is there. So this is excited triplet. Again depending on energy, there is excited triplet first, here excited triplet second, and here excited triplet third. So excited singlet, excited triplet, and this is your ground state. So let us consider, this is your ground state. So this is your ground state. So ground state, and this is your excited state, excited singlet, excited triplet. Excited triplet is lower in energy due to high multiplicity, excited singlet is higher in energy due to low spin multiplicity. Again there is a transition. So this electron, by absorption of radiation, that is, if you consider by absorption of h mu, it will goes into this first excited state, it will goes into this second excited state, or it will goes into the third excited state by absorption of radiation. Okay, by absorption of radiation. And there is a different phenomenon. So excited singlet, excited triplet, lower in energy. If a molecule or atom or electron goes into the excited state and we know that excited state is highly unstable when excited state atom, molecule or electron when goes, it is excited state is highly unstable, so it will try to return to ground state. When the electron or the atoms or molecules returns to the ground state, it will emit certain radiation. It will emit certain radiation in the form of light. Then the phenomenon is called as fluorescence. So the third point in Jablonski diagram is a radiative process and non-radiative process. If the electron is present in ground state, goes into the excited state, when it will return to the ground state, it will emit certain radiation. It will emit certain radiation. It will emit certain radiation, and this phenomenon is called as fluorescence. This phenomenon is called as fluorescence. So, molecule present in ground state absorb light radiation, goes into the excited state and return into the ground state with emission of radiation. This phenomenon is called as fluorescence. Fluorescence is observed from excited singlet state to the ground state. So, fluorescence is observed from excited singlet state to the ground state. Also, the fluorescence can be occur from excited singlet second to ground state. So, fluorescence occur in excited singlet state, that is the electrons or atoms goes into the excited state, return into the ground state with emission of radiation. So, in this case again the electrons, atoms or molecule goes into the excited triplet state, again they return into the ground state, again they return into the ground state with emission of radiation. Then the phenomenon is called as fluorescence. Then the phenomenon is called as phosphorescence, that is excited triplet. This is your excited triplet, first, second, third, and the phenomenon is called as phosphorescence. Phosphorescence. So the fluorescence and phosphorescence is same, but the phosphorescence, it is called as a delayed fluorescence. It required more time as compared to fluorescence. So fluorescence occur from excited singlet state to the ground state, while the phosphorescence occur from excited triplet state to the ground state. So both the process are considered as a radiative process, because in both the processes the radiations are emitted out or the light is emitted. Therefore, it is called as a radiative process. So fluorescence and phosphorescence both are radiative process. When the electrons, atoms or molecules when return into the ground state, it will emit certain radiation in the form of light, and therefore these processes are considered as a radiative processes, that is fluorescence and phosphorescence. Fluorescence occur from excited singlet state to the ground state, while phosphorescence occur from excited triplet state to the ground states. Another possibility of deactivation is that a atom or molecule, if atom or molecule, if it is present in excited singlet third state, it will return into excited singlet second state. So from excited singlet state to excited singlet second, or excited singlet second to excited singlet first, this kind of transformation, it is called as internal conversion. So this is called as internal conversion. This is called as internal conversion. This process is called as non-radiative process. The internal conversion, that is from excited singlet third to excited singlet second, the transformation is called as non-radiative process, because no radiation is given out when this transformation takes place. Therefore, this internal conversion is a non-radiative process. So in this case, lot of heat is removed. So it is non-radiative process, excited singlet third to excited singlet second, or excited singlet second to excited singlet first. Such a kind of transformation is occur, then it is considered as internal conversion with no change in spin multiplicity. यहाँ पे spin in this case the spin multiplicity does not change. So this is called as internal conversion. In this case, if we consider the another process of deactivation, that is if you consider this is your first, second and third excited singlet state, and this is your first, second and third, that is your excited triplet state. This process, that is excited singlet third to excited singlet second, is called as internal conversion. It is non-radiative process, no emission of radiation. Another possibility is that the excited singlet state, if the molecule is present into the excited singlet first, it will goes into the excited triplet first, or if the molecule is present in excited singlet second, it will goes to excited triplet second. Such a transformation is called as inter-system crossing. Such a process is called as inter-system crosses. This inter-system crossing is spin forbidden because the spin multiplicity in this case is 1. In this case, the spin multiplicity is 3. So this transformation, it is not spin allowed, it is spin forbidden, but also the interaction or the transformation is spin forbidden, but in many cases this is also the process, or this is also the transformation for deactivation. So in certain molecule shows inter-system crossing, it will transfer from excited singlet first to the excited triplet first, or excited singlet second to excited triplet second. So this process is called as inter-system crossing. So this is also a non-radiative process. So in this transformation, no emission of radiation, but in this case the spin multiplicity is changed. In internal conversion, there is no change in spin multiplicity, but inter-system crossing, in inter-system crossing transformation, the spin multiplicity is changed. It is spin forbidden, but many molecules shows inter-system crossing to reduce the energy and get deactivated. So this is regarding to the Jablonski diagram for the process of deactivation. Jablonski diagram consists of excited singlet state, excited triplet state, then it consists of ground state, then it also consists of internal conversion, it also consists of inter-system crossing, it also consists of fluorescence, phosphorescence. So one by one we discuss all these points, that is what is fluorescence, what is phosphorescence, what is internal conversion, what is inter-system crossing. So fluorescence, when atoms goes into the excited state, return to the ground state with emission of radiation, then the process is called as fluorescence. Fluorescence generally occur from excited singlet state to the ground state. Again, we discuss the second important phenomenon, that is phosphorescence. Phosphorescence and fluorescence is one and same, but the phosphorescence is delayed fluorescence, so it required lot of time. So phosphorescence, it is occur from excited triplet state to the ground state. It is occur from excited triplet state to the ground state. Another important process of deactivation is internal conversion. In internal conversion, there is no change in spin multiplicity. It is non-radiative process. So the molecule present in excited singlet third to it is goes into the excited singlet second, or second to first, then it is called as internal conversion. And if there is a transformation from excited singlet state to the excited triplet state, that is excited singlet first to the excited triplet first, then this process is called as inter-system crossing. So this inter-system crossing is spin forbidden, but in many cases, or in many molecules which undergo photochemical reactions, this is also a possible route for transformation of energy, or this is also a possible route of deactivation. So this is regarding to the Jablonski diagram, and the processes are involved in Jablonski diagram. that is excited singlet, excited triplet, then fluorescence, phosphorescence, internal conversion, inter-system crossing, In next lecture, we will discuss what is quantum yield and what is the causes of low quantum yield and high quantum yield. Thank you.